Electric dipole. How we define electric dipole? Any two-point charges, if satisfy the relation q1 plus q2 equals to 0 and are separated by a small distance, they constitute an electric dipole. Which means what? The charges should be equal and opposite. Just for example, say it's a H plus Cl minus. That's what it's an electric dipole. Say Na plus Cl minus. That's what an electric dipole. So any two-point charges, if separated by small distance and satisfy relation q1 plus q2 equals to 0, they constitute an equivalent. They constitutes an electric dipole. We also define a term called electric dipole moment. Electric dipole moment. What is electric dipole? We represent with the PE, because the same way we also get the magnetic dipole moment will represent by the PM. So PE is what's electric dipole moment. And what is this equals to? It's a magnitude of charge into separation between them. Magnitude of charge into separation between them. Of course, is SI unit. SI unit will be its Coulomb meter, and it's a vector quantity. It's a vector quantity. So what will be the direction? We'll take it from negative to positive charge. It's a negative to positive charge, which means if you have a negative minus q charge and plus q charge separated by distance, so we'll say the direction will be from negative to positive charge. Okay, say I just defined any assembly where the sum of charges is 0. Just for example, let us say this is charge minus 3q separated by distance a. There's another charge q, and this is plus 2q at a distance 2a. Now the question can come, find electric dipole moment of this assembly, resultant electric dipole moment for this assembly. We can see here is two dipoles. One is minus q with plus q. That's one dipole, and its direction is from negative to positive. Let's call P1. What will be the P1? P1 will equals to, it's a simply q into a. Similarly, minus 3q divided minus q and minus 2q. So this minus 2q with plus 2q will be another dipole, and this direction is from negative to positive. Call it P2, and that P2 will be, it's a 2q into 2a, which is 4qa. Obviously P2 is more, so what will be the resultant dipole moment then? The resultant dipole moment will be, it's a P2 minus P1, which is, it's a 3qa, and in the rightward direction. So you can see any assembly of charges here, it's a minus 3q plus q and plus 2q, that comes out to be what? It's a 0. So this figure constitutes a two dipole. Take another example. Say this is an equilateral triangle. There is a charge minus 2q. This is charge q. This is charge q. Separated by this, they are kept at a corner of an equilateral triangle of side A. You have to find the resultant dipole moment of this configuration. If you see clearly, this is minus 2q plus q, that assembly of total charges becomes equals to 0. It consists two dipoles. One is minus q with plus q. One is minus q with plus q. Let's call P. This is minus q with plus q, and this is another minus q with the plus q. That's again its direction will be from this P. So what is this P here equals to? It's a q into a, and this two vector quantity, and the angle between them is 60. So you can find the resultant dipole moment to be equals to, it's a root over by the relation of two vector quantity, resultant of two vector quantity, p square plus 2 pp cos 60, which comes out to be p root 3, which is, it's a qa root 3. So that's the way we can find resultant dipole moment of this type of charge configuration. Now we are going to find electric field due to an electric field due to a dipole. Electric field due to a dipole. First, electric field due to a dipole. First situation we'll find in for the first case at the axial position of the dipole. At the axial position of the dipole. Axial position, it means along the axis of the dipole. Along the axis of the dipole. What is axis of the dipole? So let's consider this is minus q and plus q. This is a dipole. For convenience, we'll take the distance between them is 2a. Now, dipole moment will be, it's a q into 2a. And this direction will be from negative to this positive charge. So what will be the axis? Along the axis, we have to find electric field, let us say at point A. Say that if the question says, find the electric field at the axial position of the dipole at r distance from the dipole. So r distance, from where we'll take this from the center of the dipole to the point A. Let's say this distance is r. Now, how to find the electric field? As we know, in order to get the direction of electric field at a point, place a test charge at that point. Let's say we place a test charge here. The electric field, let us say electric field due to minus q charge, it will be, it's a q upon 4 pi. Now, because of minus q, the distance from minus q to the point A will be, it's a r plus a. It's a r plus a whole square. And what will be the direction? If you place a test charge, this test charge will attract by the minus q. So direction will be towards this E1. The same way we can find E2. This is due to charge plus q. And this will be, it's a q upon 4 pi of epsilon naught r minus a ka whole square, because distance from this point to this point will be r minus a. And if you place a test charge here, this test charge, because of plus q charge, will repel. It is E2. Now, what will be the resultant dipole moment, resultant electric field then? Resultant electric field, you can see this E2 is more, so it will be E2 minus E1. Simplify it. Let's take common q upon 4 pi of epsilon naught. If we take common, then it's a 1 over r minus a ka whole square minus 1 upon r plus a whole square, which comes out to be, it's a q over 4 pi of epsilon naught. It's a 4ar over r square minus a square whole square. Since we know it's a q into 2a, it's what? It's a p. So here we can write the resultant electric field will be, it's a q into 2a, it becomes p. So it's a p into 2r over 4 pi of epsilon naught r square minus a square whole square. That's the resultant electric field at the axial position of the dipole. Usually, the distance r from the dipole is much greater as comparison to separation between the 2 point charges. So, if we consider, if r is much greater than a, then we can neglect a square in comparison to r square. Now, what we get? We get that resultant electric field will equals to, it's a 2p, because now this becomes what? R to the power 4, r upon r to the power 4 will become r cube. It's a 2p upon 4 pi of epsilon naught r cube. This is resultant electric field at the axial position of the dipole. If we want to write in the vector form, because we know dipole moment is again a vector quantity. See, we can write it's a 2pe, it's a 2pe over 4 pi of epsilon naught r cube. Why I'm written in this? Because the resultant electric field is in the direction of the dipole moment. See in this figure, the resultant electric field comes out to be E2 minus E1 this way, and the dipole direction was also in this way. So the resultant electric field is in the direction of the dipole moment. So that is the way how we find electric field at the axial position of the dipole. Now we are going to find electric field at the equatorial position of the dipole. Equatorial position of the dipole. What is equatorial position? Equatorial position of the dipole Equatorial means at the perpendicular bisector of the dipole. Perpendicular bisector of the dipole. Perpendicular bisector of the dipole. Let's draw a dipole. Say this is an electric dipole minus q plus q. As we know, for convenient, we'll take a distance 2a. And we want to find electric field at perpendicular distance, let's say at distance r from it. Obviously, this distance is going to be square root of r square plus a square. In order to find the electric field at a point A, we'll place a test charge here. As we know, the test charge is what? It's a positive. It's a q naught charge. That's what? It's a positive. So, if we place a test charge here, because of minus q charge, this test charge will attract toward this. Let's call this is E1. And what is this E1 to be equals to? It will be q over 4 pi epsilon naught into distance square, which is r square plus a square under root ka square. If we again place a test charge here, that test charge will repel because of this plus q charge. Let us call this is E2. And if you see clearly, this distance is equals to this distance. So E2 will be the same way as E1. E2 will be the same way as E1. Only the direction will be different. This will be the towards the charge. This will be away from the charge. Say this angle is theta, so this will be also theta. Can say this is theta, this is also theta. That means E2 cos theta will add up with the E1 cos theta. And E2 sin theta will cancel by the E1 sin theta, because E1 and E2 are equal in magnitude. So we can write the resultant electric field will equals to it's E1 cos theta plus E2 cos theta, which is nothing but is equals to, since E1 equals to E2, you can say it's a 2 times of q over 4 pi of epsilon naught r square plus a square into cos theta. See in the diagram, what is cos theta? Cos theta will be a over this hypotenuse. So this is a over r square plus a square to the power of 1 by 2. Q into 2a, this becomes what? This becomes the electric dipole moment Pe over 4 pi of epsilon naught r square plus a square to the power of 3 by 2. This is the expression for electric field at the equatorial position of the dipole. If we want to write in the vector form, again vector form, before that, if we neglect a, if it is given, if r is much greater than a, if r is much greater than a, we can neglect a. That means we get the resultant electric field will equals to it's a Pe upon 4 pi epsilon naught r cube. Interesting thing is, you can see at the equatorial position of the dipole, we get electric field at half the value of the electric field at the axial position. At the axial position, it was coming 2 PE upon 4 pi epsilon r cube. If you want to write in the vector form, now you have to see, again go to the diagram. See, the direction of electric dipole moment is negative to positive charge, whereas the resultant electric field is coming opposite to the direction of the electric field. So, how we write in the vector form? We'll write it's a negative of the PE vector, because resultant electric field is opposite to the direction of the dipole moment. Now we discuss one more case. Say this is an electric dipole. It's a minus q plus q. Separation is 2a. We want to find at r distance from the dipole, at a point A at angle theta from the dipole moment. Here is given if r is much greater than A. You have to find electric field at r distance from the dipole, okay, at angle theta from the dipole axis, by considering r is much greater than A. Okay, as we know, because of the point charge q at r distance, what is the electric field at point A? Electric field at a point A is, it's a simply q upon that constant 4 pi epsilon naught into r square. What is the electric field due to minus q charge at r distance from A? It is again the same value, q upon the 4 pi epsilon naught r square. The only thing will be what? It's a direction, because here if you place a test charge, it will attract towards this. So here we'll say, because of the negative q charge, electric field will be towards minus q, whereas here if you place a test charge, here it will repel. So here we'll say electric field will be away from plus q charge. So in this case, this is minus q charge and plus q charge, and distance from RA you have to find. You can take so many methods. You can also find this distance. So you can find, by that way you can find the electric field at a point A. Or for this solution, just view my next video.